All right, so like I said, conservative, non-conservative forces. So far, we have done work with conservative forces, so mainly gravitational potential energy, right? Yeah, gravity is a conservative force. And what we've been saying, because we have just conservative forces, we have been saying that our change in gravitational potential energy, so delta GPE, change in gravitational potential energy, is equal to the change in kinetic energy. Right? Everybody agree with that? That's what we used yesterday to do that real quick example where we had something falling down and we wanted to calculate how fast it was going when it hit the ground. Because using this was a lot easier than using our kinematics equations. Okay? So the nice big long equation, the 1/2 at squared plus v naught t plus x naught. This was a lot easier than that one. Everybody good? Okay. This is only going to be true when you have just conservative forces. Okay, so this works for something in free fall because all we have there is gravity. We're ignoring air resistance, we're ignoring every other thing that might affect it. So we're only worried about gravitational potential energy and that turning into kinetic energy. So this will work every time for things in free fall. Good? Where we can't just worry about this is going to be when we start talking about air resistance or friction or any of those other forces. Okay? So when we start adding in non-conservative forces, this will not work. So make sure you know, only works with conservative forces. Okay? Now, we have a very, very, very similar equation that's going to work with our non-conservative forces. Everybody good with that? Not going to be the same, but it's going to be very similar. If you guys wanted to look at this in your textbook too, this is going to be kind of the range between pages 113 all the way to like 120. So if you are interested in looking in the book for that, that's kind of where this section is going to be. Okay? So to figure out how we can get our non-conservative forces into this, let's go back to our definition of work, right? Now, we can write something that's pretty simple, pretty darn likely to be true. Our work that is done, or the total work done, I've written it as work total, so W sub T, is going to equal the work done by conservative forces, okay, plus the work done by non-conservative forces. Good? All right, the other thing we can say is that the total work done is going to cause a change in kinetic energy. Okay? So this whole thing is going to equal our change in kinetic, not kinetic energy. There we go. Everybody agree with what we said so far? We haven't really said anything earth-shatteringly different than before, except for we've added in this term of non-conservative work, or work done by non-conservative forces. Everybody good? Okay. In most cases, what do you think our work done by a conservative force is going to involve? Gravity. Okay. How do we calculate gravitational potential energy? Okay. So this is going to be generally our gravitational potential energy, which is mass times gravity times height. Okay. Everybody good? So when we kind of move this stuff around, we actually find something very, very similar to what we had before. Let me write what we had before off again. Actually, I guess technically this is not 100% correct. It should be. Right, so our sum of our energies is actually equal to 0. So that there is going to be a little bit of a negative sign difference between those two, but it's almost the same thing, right? Yeah. Okay. So we have that. What we have now is going to end up being our non-conservative work is going to equal the change in gravitational potential energy plus our change in kinetic energy. So pretty much the same thing, right? The only difference is instead of writing 0, we write our non-conservative work. Okay? Now, for all the cases that we've done so far, we have actually been using this equation. We just haven't talked about non-conservative forces and haven't had any non-conservative forces involved. So our work done by non-conservative forces is, of course, going to be 0, right? Because if you don't have any non-conservative forces, there's no forces to do work, right? Okay, so this equation here is the same as this equation here. This equation, we're just assuming we don't have any non-conservative forces. Are we good? Any questions? No? Okay, so we are changing our equation just a little bit, not much, but just a little bit, so that we have this work done by non-conservative forces in it. Good? Now, part of the reason why I'm going through this so thoroughly is because this adds a lot more that you have to think about, okay? Now we're going to have to look at our equations and first ask, hey, are there non-conservative forces? Do I need to worry about this? And then we need to figure out if those non-conservative forces do work. Good? Yeah? So, a great example of trying to figure out what is going to actually do work is if we had somebody swinging on a rope and then like swinging into water. Okay, so you've got like a rope swing. You're going to jump off of like a hill or something or a tree. Generally it's a tree most of the time. And then you're going to swing out over the water and fall into the water, right? Yeah? All right, what forces are acting on the person while they're swinging on the rope? Okay, we've got gravity. Is gravity non-conservative or conservative? Conservative. It is a conservative force. Okay? What other forces are acting on it? Or on the person? You're swinging on a rope. Do you think that rope is applying a force to you? Probably. Okay. So we've got the force from the rope or the tension force. Do you think this is conservative or non-conservative? It's non-conservative. So this is going to fall under the category of how I so eloquently described it yesterday of all of the other forces where you're just like pushing on something. Okay? Most of your contact forces like that are non-conservative forces. Good? So this is a non-conservative force. All right. We are going to not ignore anything in this case. So what else is going on, do you think? Air resistance. Do you think air resistance is conservative or non-conservative? It is definitely non-conservative. Okay, so air resistance is definitely a non-conservative force. Okay, it's not even going to be constant this whole time, which will make it more exciting. Okay, now this one we're good with, right? This is a conservative force. We know how to calculate that. All we need to know is how high he started out and how low he was when he hit the water, right? That's all we need to know. We're good with this one. So we're not going to worry about this one right now. Okay? Now, with these two, we're going to need to figure out if they do work. Okay? Because non-conservative forces won't necessarily always do work. Okay? So, how did we tell if something did work? Okay? So, if it moves, but there was a equation that we had. You remember when we had like the example with the suitcase and we were pulling the suitcase kind of up, but we said only the horizontal part of it does work? You vaguely remember that? Yeah? What was that equation?
F cosine theta.
Okay, so F cosine theta. All right, I think the full equation was that, right? Yeah. So we can use this equation for any force. It doesn't have to be conservative. It can be non-conservative or conservative, okay? With our tension, right? Let's draw a picture. Here's our rope. Here's our person holding on to it. As they're swinging down into the water, apparently like Tarzan, okay? All right. What direction is the force on the rope going? Okay, it's going to go along the rope. It has to. So our force here goes this direction. What direction is our motion or our displacement or distance? It's going to curve, but at every moment, it's going to be tangent to the circle the person's moving along. Okay? Since it's tangent to the circle, what angle is this? It's a right angle. It's 90 degrees. What's the cosine of 90?
0.
It's 0. Okay, so the cosine of 90 is 0. That means that when you have a force that's perpendicular to your motion, it does no work. Good? Okay, we kind of talked about this a little bit when we talked about a satellite going in a circular orbit. Okay, gravity did no work in that case because the force of gravity was perpendicular to your motion at every point. Good? So, in this case, does tension do any work? No. So tension does no work. This marker is not working very well. So we really don't have to worry about tension much. Okay? What about air resistance? What direction is air resistance going to go? It's going to go opposite your motion. Okay? So here, we've got a force that's going 180 degrees or the negative direction here. Okay? Is this going to do some work? What's cosine of 180? It's negative 1. Okay? So cosine of 180 is negative 1. So that should tell you with this equation, we actually don't need to worry about our negative signs. The cosine will give that to us. But 1 is not 0, right? Yeah, 1's definitely not 0. So that doesn't make this 0. So our air resistance is going to do some work. Good? Now, you guys don't know a good equation to calculate your air resistance. It is a fairly complicated equation, so we're not actually going to calculate the work here. This is probably one that you would want to use calculus with because this is a non-constant force. And so integrals would really be your friend in this case. Okay? And we'll talk about why that is in a little while. I don't want to quite get to that yet. Okay? Good? So we're not actually going to calculate this, but this is a really good example of how you would go through and figure out what work you need to write down. Okay? So here we know how to do gravity. Gravity is good. It's a non-conservative force. Nice and easy. Tension, because it is at that right angle, not going to count it. Okay? So this isn't going to count. Your air resistance, right, is in the opposite direction. That is going to produce work. And so this is going to be a problem that we can't really easily do. Okay? Now, if we were ignoring air resistance, we could do this just fine. And we would know why we could ignore our work from our non-conservative force, right? Everybody good? Any questions? No? Okay. So adding in this non-conservative force means that you have to think a little bit more, but a lot of times it's not really going to be that much harder. Because a lot of times your work is difficult to calculate with your non-conservative forces, I think every single problem that I saw in the book either provided an equation to calculate the non-conservative force, or it told you just like a certain amount of work the non-conservative force did. Most of them just told you a number. Okay? Everybody good? Okay. So let's say that our person started from a nice high embankment here and is swinging down into the water down here. All right, we'll do this tomorrow. Have a good day, guys. Good luck with your slides.